Well, welcome everybody to our first seminar of the semester. It's a pleasure to have today with us Dr. Lu from the Statistics Department at NC State. Dr. Lu is a professor in the Department of Statistics at NCSU. His broad research interests are in biostatistics and high-dimensional data analysis, machine learning and reinforcement learning. He's an associate editor for many different statistical journals, such as Biometrics and Statistica Sinica and all. He's an elected fellow of the American Statistical Society Association and an elected member of the International Statistical Institute. And I've known about his work actually for quite a while. I wanted to invite him for quite a while, and now is a good time on a snowy day in North Carolina. It's a pleasure to have him here, and he'll be talking to us about some of his work in treatment regimes in health sciences. Thank you for coming, and the floor is yours.
Thank you. It's my greatest pleasure to be here to give a talk, especially in such a snow day. And today I will talk a little some recent projects my group did in this statistical machine learning method for optimal treatment regimen. That is a big research area in the so-called personalized medicine. Okay, first I give a little bit background about the optimal treatment regimen. Just be brief. The traditional treatment regimens, usually people want to find the best treatment that works for everyone. So that's what we call the one-size-fits-all, kind of treatment regimen. But nowadays, in modern clinical trials, people find patients have big heterogeneities in response to different treatment. So people want to design the so-called individualized treatment regimen, which is a set of treatment decision rules that aim to account for individual heterogeneity in many different aspects. For example, in clinical parameters, in genetics, in social, environmental, behavioral characteristics. We want to maximize long-term clinical outcomes. For example, for cancer patients, we want to maximize their 5-year or 10-year survival probability. And we want to reduce the risk for over or under treatment for individual patients. And this developed statistical machine learning tools for optimal treatment decisions have attracted a lot of attention recently, especially for treating complex disease like cancer, AIDS, and mental disorders. Here I first start a few examples like motivate us our different studies in these areas. The first example is a little bit older example. This is from the AIDS study. This is the ACTG 175 data. And this is a okay. Thanks. Let me see.
It's not a pointer. It's a mover.
Oh, it's a mover. Okay.
Okay. Maybe it doesn't work.
Doesn't work here.
All right.
Yeah. Okay. Anyway. Yeah, so this is from clinical trial studies, and we consider HIV-infected patients with CD4 count at baseline is between 200 and 500, and the patients are randomized to 4 different treatment groups, and besides the treatment assignment, people also collected the baseline clinical parameters of patients, such as age, weight, Konofsky score, CD4 count at baseline, and so on, And there are a few different primary endpoint of interest. One is the CD4 count at 20, around 20 weeks, post-treatment. People want, after they give the treatment, people want to increase the CD4 count. The second one is a more like a long-term endpoint of interest is a time to event. That is the first time a patient had a decline in their CD4 count, say at least 50%, or an event indicating progression to AIDS or death. So this is a survival time to an event. And from the past literature, people find the middle two treatment, this is the people call the combination treatment, is more effective. In other words, is uniformly better than this single treatment, the first one and the third and the last one. However, when you compare these two, okay, combination treatment, that is ZDV plus DDI and ZDV plus ZAL, there's no much difference. When you look at the survival curves, they cross each other, so there's no one is dominant than the other one. Here, we try to look at it a little bit closer. We want to do a stratified analysis. Here, we use age to stratify the data and into two different groups. So here, okay, that is we show, okay, the stratified analysis. The left-hand side, we use age to do the stratifications. And in the data, 34 is the median age of the data. So we divide the data for age less or equal than 34 and age bigger than 34. And then we plot the Kaplan-Meier curve, that is the estimation for the survival curve of the patients for two different groups. You can see for the younger patients, the treatment zeros, okay, we coded like the one of the treatment, combination treatment is treatment 0, the other one is treatment 1. The treatment 0, the blue curve, is uniformly better than treatment 1. And it means the patients, the younger patients who receive treatment 0 have a better response, have a bigger survival, okay, probability. However, on the other hand, for the older patients, okay, the patients with age, okay, bigger than 34, the observation reversed. The patients receive treatment 1 have, okay, better survivals compared to treatment 0 uniformly. So this is a kind of very common phenomenon in medical studies. Patients here is, in terms of age, they have heterogeneities in response to treatment. By, okay, using this kind of information, okay, we can decide, okay, which treatment is best suitable for which kind of, okay, individual patients. For here, very simple, okay, younger patient, the treatment 0, okay, is better, but for the older patient, the treatment 1 is better. But here, consider we have many different, okay, clinical parameters, and how can you define, how can you develop a decision, a best decision to maximize, okay, the utility you want. Here, okay, is the survival rate, survival probabilities. That is a difficult question and a challenging questions. And our first kind of research, we want to develop this kind of statistical and machine learning tools to find the best treatment decision rules, and also try to make inference, okay, how, in what kind of sense you say the decision rule you find is the best. So we want to do some inference for this kind of problems. So that is our first examples. However, this medical studies is in many times more complicated than just this single, okay, treatment decisions. And in many of the studies, treatment are given at different time points. Okay, the future treatment assignment will depend on how the patients will respond to the previous treatment. So this is given in a dynamic versions. That is the second example is called is from the study, and this study is from a so-called sequential multiple assignment randomized trial. It's called SMART, okay? Sequential multiple assignment randomized trial. And in this, okay, studies, people want to compare the effectiveness of different multi-level treatment options for patients with major depressive disorder. This is the MDD disease, and you can see this is okay diagram for the treatment designs. At the beginning, the level 1, all the patients were given the same treatment is CIT. And then, based on the patient's response, for those, okay, who don't have a good response, in the second level, I will switch to other treatment options. For the patients who have a good response, we will augment the original treatment with some, okay, supplements. Okay, so that is the level 2 treatment. When I do this assignment, it's a randomizations, but this randomization depends on your past, okay, response histories. The same thing from level 2 to level 3, level 4. You can also, based on the previous, okay, response, I can either decide switch or augment. Okay, the final stage is all switch to this treatment. But between level 2 and level 3, for a stable group of patients, okay, we can also decide, okay, intermediate step, whether you want to switch to the treatment or another treatment or not, depends on the response. This is a very typical in modern clinical trials. People design, this is SMART, okay, and the future treatment assignment will depend on the historical data and the historical, including the historical clinical information, the historical treatment history. We want to use these information to design best with so-called dynamic treatment regimen to maximize, okay, the utility we are interested in. For example, in this study, the response we are interested in is the symptomatic status, which is characterized by the QIDS C16 scores. The smaller the score, the better, okay, the behavior of the patients. So that is our target. And for this data, we collect a lot of predictors. For example, more than 300 predictors from various aspects, including the answers in psychiatric diagnostic screening questionnaires, the rate of depression, the patient-rated inventory of side effects, and the demographic factors. All these kind of informations are collected along the studies, and then we want to make use of this information to guide us to do the best treatment decisions. And the study objectives, okay, there are a few. One objective I just mentioned, we want to determine the relative effectiveness of different treatment options at different levels. So back to our diagrams, we want to design a dynamic treatment regimen, okay, to maximize the utility of your interest. And how to design this one? People usually will do this dynamic programming, do the backward inductions. From the last stage, you go back to your previous stage, try to find the best treatment path, okay, to maximize the quantity of your interest. The second question is particular for this kind of data applications. You have a lot of predictors. Not all of them are helpful to help you to do the treatment decisions, and also the number of predictors are very close to the sample size. Usually in the medical studies, we don't have big sample size. In these studies, just hundreds of patients here. So the number of predictors is about the same scale of the sample size. So how you make a reasonable inference? Then we want to introduce this so-called sparsity do the variable selections. So we want to identify predictors that are important for treatment prescription. Then we want to derive some so-called sparse decision rules. So this is a variable selection problems for dynamic programming. That is the second research questions, okay, we are interested in. Okay, I will discuss later. The third one is another example, is a different, okay, kind of research questions. This is from the schizophrenia studies. It's a multi-center randomized controlled trials with 18 months follow-up, and we want to examine the effectiveness of the cognitive behavioral therapy for patients with schizophrenia. And here we have a few treatments to compare. One is the so-called CBT, the cognitive behavioral therapy plus treatment as usual. The second one is the supportive counseling plus the treatment as usual, and then the treatment as usual. So these are three very popular treatment. And then the response here is the reduction in the PNSS score. So that is the response. The larger of the reduction, the better of the outcome. And the X, they also collect a bunch of cohorts, but in this study we only consider two. One is the baseline, PNSS score. One is the log durations of untreated psychosis. And over 400 patients initially enrolled in 11 different mental health units in England, and we have complete data for about 135 patients. However, for this data, the data collected mainly from 3 different geographical locations. One is the Manchester, Salford area. One is the Liverpool. The third one is from the Nottinghamshire, these areas. And in the history, in the literature, people found patients from different geographical areas have significant, difference in response to treatment. So the data you got, from different, this kind of, locations have big heterogeneities. When you do the treatment decisions, how can you take into account this heterogeneity in the data? How can you derive one single treatment decision rule that can work for different geographical locations? So that is the, optimal treatment decision with heterogeneous data. So that is the third, kind of research questions, we are interested in. So that is a kind of a summary of the research problems, in the recent years we are doing, and also that's what I will talk about in today. So the first one is a kind of develop statistical and machine learning method for OTR, for optimal treatment regimen, and then to do its associated inference. In particular, in this talk, I will discuss a recent development from our group. It's called concordance assisted learning and the sparse concordance assisted learning, SPARSCO. And the third one, the second problems we want to study is to do this variable selection and the dynamic programming for the optimal treatment decision. This is related to this SMART trial. You have a dynamic treatment regimen path, and in particular, our group developed a penalized A-learning approach. How can you do these things? And the third one is to derive OTR with heterogeneous data, and from our recent work is the maximum projection learning. We propose a new way to do the treatment decision with heterogeneous data. So I will do it one by one. But before that, I first give a quick brief mathematical framework for the setup. This is done at a very simple framework. In the very simple situations, we only have one single treatment decision point at the baseline, but this can be extended. Y is the real value response, and A is the treatment indicator, you received by the patient. For example, you can consider treatment either 0 or either 1, a binary treatment decision, but we can consider more than 2 treatment decisions. And X is the predictor as the input, you want to using the patient's characteristics in X to help you to the treatment decision. And our treatment decision loop or treatment regimen G, which is a functions, function of what? Which map the covariance space to the treatment space. So you tell me the patient's X, my return is either 0 or 1. Give you which treatment this patient should take. So that is a treatment decision loop or treatment regimen. And what is our goal? Our goal, we define this one all through the causal, the causal inference. So we introduce the so-called potential outcome, Y star A, What is Y star A? Which is a potential outcome, that would result if a patient were assigned to treatment A from the treatment subset. This potential outcome may or may not be observed, depends on whether you actually receive the treatment is the same as this A or not. If they match, then you observe, otherwise you do not observe. But the goal is what? The mathematical framework. We want to find the treatment regimen G, these treatment functions, to maximize the expected potential outcome Y star if all the patients are treated using the same treatment regimen G, right? So if all the patients I assign the treatment according to my G functions, I want to study on average what is the expected potential outcome. I want to find the function G to maximize that. So that is a math framework, and with this framework, we can do estimation, we can do inference. So that's important. And based on this one, in the literature, in recent years, there's a very popular approach. People try to estimate the optimal treatment decisions. This is the so-called value-based optimization method proposed by Zhang et al. In 2012. And this method, they try to propose a non-parametric estimate for the function, for the target of your interest. You want to maximize the mean potential outcome. Then I found the estimate to maximize. The idea is simple. They consider this is a missing data problem, as I mentioned. If the actual received treatment AI is the same as the treatment regimen, like the treatment assigned by the G, then your Y star is observed, which is YI. If AI is not equal to the treatment, the treatment assigned by the G, then the Y is not observed. So this is a missing data. If you consider this kind of estimations, I will divide by the probability AI equal to G. So the denominator is the probability these two things match. So we do this inverse, the so-called inverse propensity score weighted estimate. It's a very popular method, for handling missing data. This pi is the so-called propensity score. That is the treatment assignment probability given patient's covariance. So people can show that this Vn head is a consistent estimate for this Y star. We don't need to assume any model as long as you can model the propensity score. That means that you can model the treatment assignment. This is not difficult in randomized trial. We know by design what is this kind of randomization probabilities. So this can be easily calculated. So you can see, we have this non-parametric estimate. Then we want to find the function G to maximize that. And usually, in medical applications, people prefer some simple treatment decision rules. People, for example, will consider this linear decision rule. The G equal to the beta transpose X bigger than alpha, okay? So we want to search parameter beta and alpha to maximize my estimate the value functions. So that is the, okay, terms here. And then due to some identifiability issues, we want to, okay, normalize, okay, beta alpha have a norm 1. So for that, this is just for identifiability issues. And this method, okay, have certain advantage. The one very biggest advantage is its robustness, okay? That means we don't assume any model assumptions. I didn't model the Y. We just non-parametrically estimate the value functions and then find this alpha and beta to maximize. So it's very robust to model misspecifications. And also, even your true decision rule is not given by these linear functions. Doesn't matter. This method still is meaningful. It still can find the best linear decision rule, okay, to maximize the value function. So still is the best thing you can do in the function of linear decision rules, okay, in the class of linear decision rules. So they have their very good advantage, robustness. However, they also have certain disadvantages. One thing is this, okay, V hat functions is a very discrete functions. It's very challenging to maximize, especially when the X dimension is relatively large. Okay, usually it's very challenging. And in the original work, they can only, okay, maximize over dimension less than 10. Okay, if bigger than 10, usually it cannot work very well. So it's very challenging optimization problems. The second one, okay, the properties of beta and alpha are very difficult to study. They have non-standard, okay, convergence rate. The convergence rate is slower than the root n convergence rate. That's very different. That's very challenging, okay, inference problems. And in the literature, okay, people propose a little bit of variations, okay, of this kind of value-based optimization method. The bigger, okay, motivation for this one is the optimization is difficult due to this discreteness of the indicator functions. Then how people will do, people want to link this kind of optimization to the classification problems. People found, okay, if you want to maximize this estimated value functions, it's equivalent to minimize this kind of, okay, loss. And when you look at this loss, actually, this is a weighted classification problems. So AI, you can consider that is my label. And the GXI, that's your boundary classification functions. And the YI divided by the propensity score function, that's my weight. So this is a weighted classification problems. And for weighted classification problems, in the literature, people have many good, okay, algorithms. For example, I can approximate this indicator function by a hinge loss function and using the weighted support vector machine, okay, to do this optimization. This is a convex problem. It's much easy to handle and can work with the high dimension. So that is one proposal. It's called outcome weighted learning, called O-learning. And they kind of replace this indicator function by a hinge loss and then do this weighted classifications and then do the optimization. This provides an approximate solution for the original optimization problem and can be extended to very high dimensional. So that is one, okay, procedure here. However, they still suffer, okay, other, okay, disadvantages, okay, of the value-based search method. Then here comes our ideas, okay. Our idea, we want to propose a new concept in treatment decisions, and our idea is, okay, let's consider, okay, your value function expectation of Y star GX. After a little bit elaborations, we can see this value function can be written in this way. And in the value-based, okay, optimization method, since we want to maximize that terms, which is equivalent to say I want to maximize the first term because the second term is a constant. And then to maximize these terms, in other words, okay, we want to assign a subject to treatment 1 if Y star 1 minus Y star bigger than 0 and 0 otherwise. This is intuitively reasonable because if this Y star 1 is the, okay, potential outcome if the patient is given treatment 1, Y star 0 is the corresponding parameter given treatment 0. If Y star 1 is bigger than Y star 0, of course, I should give treatment 1. Our convention is that the larger the response is the better. Okay, that's by convention. So that is the treatment assignment when you directly maximize the value functions. However, our ideas, instead of consider just one patient, okay, how about we consider a pair of patients? So we consider any two subjects, I and J, and we consider their benefit of receiving treatment 1 compared to treatment 0. So that is YI star 1 minus YI star 0. That's the benefit. Okay, you receive treatment 1 compared to treatment 0. If this benefit for subject I is larger than for subject J, a good treatment regimen should be more likely to assign subject I to treatment 1 compared to with subject J. We want to maintain this kind of concordance when you do the treatment assignment. So that is what we saw, the concordance learning. And when you have a linear descent rule, that means what? Your beta xi should be bigger than beta xj. Okay, we want to encourage this kind of treatment assignment concordance among any two patients. So that is the paper we wrote. Okay, we define a concordance function. So you can see that's two pieces. The here is the difference. Okay, compare the treatment benefit for subject I when they receiving treatment 1 compared to subject J. The larger the difference, we want to encourage your beta xi should be bigger than beta xj. So that is a concordance, more like a rank, correlations between this benefit difference and this kind of rank between beta xi and xj. Okay, so let's redefine a concordance function, and then in our concordance learning, we first find the beta star to maximize this concordance function. That's the best thing you can do in terms of concordance. After you have beta star, then we just search for one-dimensional threshold values to maximize the value hand functions. This alpha is very easy to search because it's only one-dimensional. So I do a discrete search, I can easily find alpha star. Put together, our core learnings is given by this linear descent rule. Okay, and in particular, the beta star X, we have a name we call the prescriptive index. The reason we call the prescriptive index, we can use this index to rank patients. If beta star X is larger, this patient should be more likely to give treatment 1. Otherwise, should be more likely to give treatment 0. So it's a prescription index, give the ranking of patients. So that is the kind of idea behind this one. And then with this idea, the next question, can we use data to estimate this one? And turns out, yes, we can estimate this concordance function using the data. And one bigger observation is through this propensity score adjustment, we can show that this term's conditional expectation is exactly equal to the difference of these two conditional mean. And using this one, we can construct a consistent estimate of CN hat. I will not go to any more details about that. And anyway, in this paper, we showed, as long as you can model the propensity score correctly, this is a consistent estimate of your concordance functions. Now, I can find my beta to maximize, this CN hat. And then after you have the, beta hat star, I can do the one-dimensional search for threshold value to maximize the value functions. So that's our concordance learning estimation result. But then the question is why you think this is better, than the directly value search method. That is related to the CN hat properties. This CN hat, when you look at the statistics, it still involves these indicator functions. It's still a discrete function for beta. However, this is the use statistics of order 2. This CN hat, the smoothness is much better than the original value functions, and we can show that. This function is much easier, to find the optimizations and with very nice properties. And this can be illustrated, from these theorems. And we can show that, by maximizing the concordance functions, the maximizer beta hat have the standard root n consistency converge to the normal distributions. But the original value-based search, the convergence rate is much slower than root n. So the actual rate is what? That is our second theme. Because our alpha star, the initial value still, the threshold still using the value-based search to find the estimate. And then we can see, actually for this kind of estimate, we don't have the root n consistency. You only have n power cubic rate. So it's much slower. And the distribution is not a normal distribution. It's a very complicated, this kind of argmax of a Gaussian process. So that's the value search method have this kind of disadvantage in terms of theoretically. And finally, we can prove for the value function that you are interested in, we can establish this kind of a normal distribution. Based on theorem 3, we can do all the testings to see whether one treatment regimen is better than the other treatment regimen in terms of value functions. If we have this normal distribution, we can do the formal testings. And let's see, in this, ACTG, the AZ examples, we run our core learning method, and then we can estimate all the betas, and then we can compute the p-value because we have the normal distributions, and then we found among all these 12 covariates, only the first covariance, that's age, okay, is significant. Let's match with our, okay, the picture I show you. Age is a very important predictors to guide you to the treatment selection, and our colony, okay, confirm that it's the very significant, okay, predictors. And also, we compare our colony-based method with this value-based, such as the IPSW method, using these cross-validations. Okay, we do 200 random split for data, half to train the decision rule, the other half to evaluate using the value functions. And we found, okay, the colony give you the larger, okay, value function average, the smaller standard deviations, but the IPSW method give the smaller, okay, the value function with even larger, okay, standard deviations. So the core-learning can give you higher, okay, value function with the smaller standard deviations. This all means, okay, they have a very nice, okay, empirical and theoretical properties. However, the core-learnings also suffer some kind of, okay, some of the challenges, okay. One is this discretization optimizations, okay. Even we have the older two use statistics, okay, the smoothness is better than the value search-based method, but still discrete functions. When you do this optimization, you need to try different initial values, okay. Some initial values can converge, some initial values cannot. You need to try different, okay, starting point. And also for the high dimensional predictors, okay, still be challenging. So that is motivates us to also consider a kind of a convex approximations, okay, of your, okay, core learning loss. So that is our second paper, is the sparse core, okay. After some, okay, algebra, okay, we showed, okay, the target, we want to maximize this kind of function. After some argument, we found, okay, to maximize that is the same as minimize of list quantities. And the list quantities, okay, is like before, we can link them to a minimization of a hinge loss functions, okay. So we approximate that indicator function in the previous slide at the end by these hinge loss functions. Then this is also like another weighted, okay, classification problems. However, here the label is just one, okay. We do this kind of, okay, weighted classification problems, and then we add some L1 penalties to encourage sparse, okay, of your estimates. So that is our, okay, kind of sparse core-learnings in the first step. After you have the beta height estimate, our alpha, the threshold, we still search the one that maximizes the value functions. So together is the sparse core. Okay, we approximate the indicator function by such kind of hinge loss functions, and then we can easily, okay, do the optimizations. And for this optimization, since it's a convex problems, you have many available software you can do it. For example, I can use a convex optimization package. This is called the CVX, okay. This package is, okay, you can specify and solving any convex, okay, programs. The advantage is very easy to implement. However, the disadvantage is the speed is relatively slow and requires very large memory. And some other possibilities, we can do this piecewise linear programming using the GLPK packages, and also we can use the Spingarn's method, okay, and especially the last method is good for the big data. And for our data, like the study data, okay, we found only the last method can work, okay. All other methods are too slow, okay, to work on that kind of dynamic programming. Okay, so that is the optimizations. And a little bit about the, okay, the symptotic properties we showed. So for this weighted classification problems, we can show certain kind of L2 error bound for your estimate. So we define the population beta star that minimize, okay, a population version of the loss function, and then you estimate from this sparse core-learning beta head, that's all in our decision rules, minus its true value, this L2, okay, bound, okay, L2 errors, we give an upper bound here, okay, depends on a few quantities with certain high probabilities, and based on this result, okay, we establish kind of a consistency, okay, of beta head minus beta star. And in the quantity you can see, okay, P is the number of predictors you have, and the Q is the number of true important covariance you in the decision rule, and the N is the sample size. So as long as, okay, this right hand side, this P, Q, N satisfy the relationship, like this converge to zeros, then you have the consistency in terms of L2 norm. So this one establish, okay, connections between P, Q, and N. In what kind of situations our sparse core can consistently estimate, okay, its target populations. So that is the kind of properties we studied here. And then back to this studies, okay, we run the data. Here we only consider one stage, okay, one levels. So we consider, okay, the two treatment, BUP and SER at level 2, and among them we have 309, okay, subjects, and 153 received the one treatment BUP, and 162 received the other treatment, and in total we have 305, okay, cohorts. You can see the number of cohorts is very comparable to the number of subjects, so this P is very close to N, okay? And for this sparse learnings, they, at least from our theory and from the computation algorithms, they can easily handle this kind of situations. And actually, our theory, okay, is even more than that, okay? We can handle this number of cohorts grow at an exponential rate of sample size, okay? So can allow this P much larger than sample size N situations with this kind of sparse core, okay, regressions. But anyway, when we apply this method, okay, to the data, and then the sparse core learnings, okay, the treatment decision rule, okay, they lead to an estimated value function is about -0.677. Using the O learnings, okay, that we mentioned, okay, the outcome weighted learning with the supervisor machine, weighted supervisor machine, the estimated value is only -9.46. If you assign to one of the two treatment, that's corresponding to the value functions. Then we calculate the difference, we calculate the corresponding confidence intervals. You can see, okay, our method is significantly better than the other three, okay, regimens in terms of the value functions. The difference is significantly bigger than zeros. So this is a, okay, kind of support evidence, okay, by doing this sparse core learning, we can improve the treatment decisions, okay, to get larger, okay, value functions. So that is the kind of first things, okay, first kind of project I discussed using the core learning ideas, the concordance functions to guide our treatment decisions. The second project is try to study the situations your treatment is given sequentially. Okay, you need to do a dynamic programming with high dimensional predictors. So that is the dynamic, okay, treatment regimen. Here, I only consider a simple case, just illustrate with only two treatment decision points. Okay, at the time T1, you want to give a treatment decision A1, and then using the baseline cohorts S1. After you give the treatment decision A1, you will receive the, okay, intermediate cohort as S2. Then based on all the past history informations, you want to decide the second treatment A2 at the time T2. So you will do this in this fashion. And finally, you got a response Y. Okay, so here I only illustrated with two treatment decision points, but this can be easily extended to more than two treatment decisions. And what is the dynamic treatment regimen? Now, it's just only one decision function. It's a two decision function. At the stage 1, at the level 1, you have a decision is from the baseline cohorts to your treatment space. At the level 2, not only the baseline cohorts, you have the treatment history, you have the intermediate cohort history. All together, the past information is my input. And using this one as my X, I will make a decisions, okay, 0, 1. That is at the second treatment time point, okay, you make a decision. Using all the past history, the final thing, we still want to maximize the potential outcome Y, okay. So that is kind of a setup for our, okay, mathematically, okay. And in terms of models, okay, we want to propose a model. How can you do this treatment, okay, decisions in a dynamic way? So at the final stage, Y, okay, we give a model here, okay, we so-called a semi-parametric regression model. The H2 is a baseline function, totally unknown, but we consider a linear interaction between treatment 2, okay, treatment time 2 with the, okay, cohorts, okay, Xi. This Xi, including all the past histories, okay, all the past histories, and then that is the final stage models. From the final stage model, you want to do the backward inductions, okay, do this kind of, okay, dynamic programming. So we want to find, okay, suppose at the second stage, at the second level, you do the best treatment decision in terms of what? You find the AI2 to maximize the so-called Q functions. Then that's my VI, that's my intermediate response at the first, okay, levels. So for this VI, we posit another models. Then based on this model, I want to do the decisions. So you can, this VI is computed from the second stage model, and then you carry, okay, backward.
So presumably you can't go very far in time then, right?
Yeah.
Otherwise it explodes, right?
Usually it's dynamic programming, okay. conceptually, you can go many time points, but the error easily accumulate together. The performance will become worse and worse. Yeah, yeah. Usually in medical study, we only do 2 or 3 time points at most. Yeah. So that is the dynamic programming, and then based on these 2 models, that is the best decisions you can do here. And in the literature, okay, people proposed, okay, using the robust estimating equations to estimate, okay, this model, this statistical models, and very famous, that is the proposed by very famous statistician Susan Murphy in 2003, is a GSP discussion paper. They proposed kind of like A-learning estimating equations, and I will not go to details, but this A-learning estimating can have a nice properties. It's called the double robustness properties that says, okay, when either of the propensity score model or the baseline model is correctly specified, you have consistent estimating equations for the parameter of your interest. So they can do these estimations in a robust, okay, fashions. But our problem is what, remember, our problem is the X is a very high dimensional and is even larger than the sample size. So you cannot directly solve these equations. The P is much larger than N. Okay? So we want how can you encourage the sparsity of your betas. So that is the questions we want to address here. And here we propose the penalized A-learning. This is a recent paper from our group. So in the first step, okay, since you have high dimensional predictors, I want to fit the propensity score model and the baseline covariance. I need to encourage sparsity. So add some non-concave, okay, penalty function, for example, like the scatter penalty functions, to do a penalized logistic regression and a penalized least square regression to first fit these 2 models, either the propensity score model and the baseline model. Then at the second step, I will do this so-called, okay, penalized A-learning equations. I want to minimize, okay, the L1 norm of your decision parameter beta 2 such that your A-learning equations, the infinity norm, is less equal than certain threshold. So we formulate the problem in this way, okay, minimize the L1 norm and such that the A-learning equation, the infinity norm, less than certain threshold. So by doing this one, we can find the sparse solutions that give you a closed solutions for the A-learning equations. So after you get the beta 2 hat at the last stage, the second stage here, we still need to do the backward inductions. And how we do the backward inductions, we will compute VI hat using the advantage functions, okay, which is Y plus the interaction term times the difference of these 2 indicators, okay? So if there are these two indicators, if the difference is 0, then there's no advantage. VI hat just equal to Y. Otherwise, you need to adjust it by the advantage functions. People can show that, okay, this VI hat is an estimate, okay, is an estimate of VI here, okay, it's estimate of VI here. So we can do this kind of, okay, advantage learning to using in the backward fashions. After you have VI hat, okay, in the first step, we can, in the first stage of treatment decisions, we do the same thing. We fit the penalized logistic regression for the propensity score model, the penalized linear regression, okay, for the baseline model. After we do that, we still do a penalized, okay, A-learnings, okay. We minimize your first stage, okay, decision beta 1, the L1 norm, subject, okay, to this A-learning equation and the first stage, okay, less equal than a threshold. Okay, we do this kind of optimization, and this optimization can be done using the piecewise linear programming. So we have very efficient, okay, algorithms to solve this problem, even with a very large P. Okay, this can be solved very efficiently. So after we do this one, we can do this, okay, backward inductions from the last decision time point backward to the first decision time point using these dynamic programming strategies. And this algorithm is nice, but then we want to study, okay, what are the properties of this kind of dynamic programming using these penalized A-learning equations. In particular, we want to study what is the theoretical performance guarantees for the value estimations. So our value functions, okay, this is expectation of Y star, okay, that's the potential outcome. If you consider at both stages, okay, level 1, level 2, you use the optimal treatment decisions, compare with our estimate. What is the difference here? Can you give a bound, upper bound, your estimate optimal decision rule, compare with the true optimal decision rule, okay, in terms of value function, what is the error bound there? How can you establish the result? Okay, this result, of course, depends on, okay, many, okay, properties we want to establish. The first one, okay, we estimate the propensity score and the baseline models at the second stage. We want to establish the error bound, the non-asymptotic bound. Similarly, for the first stage estimate, we want to establish the error bound. And then the error bound for the second stage decisions, okay? And the error bound for the first stage decisions. And then finally, how we target these problems. Suppose the first stage, you still do the randomization. You don't do the optimal treatment decision. But the second stage, you do the best decision, compare our estimate. What is the error bound there? Then the final thing we do, okay, if both stages you do the optimal decision, compare with our both estimate the optimal decisions, what is the error difference, okay, the bound. And we target this question in this way. Okay, the first one is the first stage, they are randomizations. We don't do any optimization. Only the last stage I do the optimizations. Then what is the difference? Okay, remember the left-hand side is always, the first quantity is always bigger than the second quantity because this is the true optimal. This is our estimate optimal. So we only give a difference to bounded above, okay, by a constant, okay, and then is bounded by this constant, and then we found, okay, our result is more accurate, okay, in some sense than the original result by Chen and Murphy in 2011, and more than that, okay, based on these intermediate results, okay, we can establish the final result, okay, that is the true value function and the true optimal dynamic regime. That's our value function and the estimated dynamic regime. So the difference, we want to establish a bound. So it's bigger or equal than 0 because this one is always better than this one, but it's upper bounded by this one. And we have some interpretations for these terms. The first leading terms, that is due to the misspecifications, okay, of your modeling. And some of the terms here, this is due to the error, okay, in the estimation of beta 2. This is due to the error in the estimation of beta 1. Some is due to, okay, the kind of this kind of penalized regressions using, okay, Danzig selectors. So each term corresponding to the error you accumulate during your estimation dynamic programming, and overall this difference can be bounded above by this kind of accumulated errors. So they can give you some guidance, okay, about this, okay, from this theoretical result. Anyway, and then we apply this one to the studies, this, okay, dynamic treatment, okay, programming. And here we consider two different levels, level 2 and level 3. And for the level 2, we compare these two treatments. For level 3, we can compare the other two treatments. So together, okay, you can have 4 combinations. Okay, this treatment at level 2 plus this treatment at level 3 and so on. Okay, you have 4 this kind of combinations. But ours is okay, dynamic regimens. Okay, we will use the patient's past history to make decisions whether I should take this one or this one at level 2. This one or this one at level 3. Okay, we will do this dynamic regimen. And this 4 is more like a non-dynamic. Okay, and then we will compare the method in terms of the value function, which is defined by here. And after I apply the penalize the A-learning among 381 cohorts, we pick 3 variables at level 2 and 3 variables at level 3. Okay, so you can see the final decision is very sparse. Even you have more than close to 400 cohorts, but only 3 variables selected at level 2 and 3 variables selected at level 3. And when we construct the value function and compare with this non-dynamic treatment regimen, the value function ours is higher than the than the other non-dynamic regimen, and the difference is very significant. The 95 confidence interval is all above 0. Okay, confirm. Okay, after you do this penalized A-learning, you find the dynamic treatment regimen that can really improve the final response. So that is the for this project, we try to derive a variable selection procedures, a sparse decision rule for this dynamic programming procedures. Okay, let's come to the last questions. We want to handle the heterogeneity in the data, and as I mentioned, in medical studies, this heterogeneity is very common, and this source of heterogeneity can come from different situations. The one is the data integrations, or what we call the meta-analysis. So results are combined from different studies, to identify similar patterns. This heterogeneity can due to study population difference, can due to study periods are different. You want to combine different studies together, they have the heterogeneities you need to handle. The second one is more like handle massive data. Okay, you want to do this divide and conquer procedures. So data is too large to fit overall models. Okay, a possible solution we divide data in several groups. This may cause some heterogeneities. Then after you have the estimate for each group, how can you combine them together? So this heterogeneity due to large scale of the data. So both are possibilities to create the heterogeneity in your data when you make the treatment decisions. And then our questions here is how can we effectively combine different treatment regimens you learned from different group of data, and how to take into account the data heterogeneities. Some simple solutions, we can just combine data together. Suppose the computation is not a problem, we just combine the data together and find the optimal treatment regimen based on the pool data. So totally ignore the data heterogeneity. That is a very naive way, to do it, and we can see, they are not good. Another way, is more like the simple divide and conquer ideas. I found the group-specific optimal treatment regimens and then take a simple average of them. So average them. This also we found may work bad for some of the groups. Now our thinking is what else can we do with this heterogeneous data, or what is a good criteria for combine treatment regimen from different groups with heterogeneity. So that's what the research questions we want to address. Here we consider this kind of model. Suppose the data is from G different groups, and the YG, the response in the group G is modeled by here. Is also like a semi-parametric regression. H is a baseline function, unspecified. A is the treatment indicator. The precise function is a monotone, transformation monotone increasing function, and inside, is a linear index function. So the treatment decision still depends on the beta G xg. Remember our goal is to maximize the expectation of Y. So the larger of the index, the larger of the response. So the best decision is still based on the linear decision. The reason we consider linear decision because it's simple, much easier to study. And then we have G different group, so their decisions are different, right? For each group, the best decision is beta G times xgj. So they are different across different group. And the objective is what? We want to find a common decision rule that works best for every group. Whether we can find in certain sense. So the idea. We can consider group-wise optimal treatment regimen. That is the linear decision function depends on the beta G in that particular group. And the overall decision, that is we want to find a common treatment decision rule. That is beta 0. And then our strategy is a two-step. We want to first search beta 0, achieve certain optimality, and then we find the C0, to maximize the value function. And how can you define the optimality for the data with heterogeneities? That comes to our main ideas. We want to define a reward functions by given treatment regimen, beta G from that particular group. Later I will discuss what are the possible reward functions you can pick. Suppose you can define a reasonable, reward functions for that particular group by assign, using the treatment regimen beta G. Then our, this kind of idea is considered as a max mean effect. We want to find the beta, to maximize the minimum reward across all the groups. So in other words, maximize the minimum reward, or we want to minimize the risk of the worst case scenario. You want to find the one treatment regimen that works for all groups. I want to see, what is the minimum reward if I apply this beta to different group? Then I want to find the beta to maximize the minimum reward. Control the worst case scenario. So that is our max mean, kind of idea. I will do it first. So the reward function we choose, we can consider, the percentage of correct decisions, compare the group-wise the best you can do, or the overall, treatment decisions. Want to control the percentage, the difference, between this group-wise optimal and the overall optimal, control the PSD. We also can control the value difference, Both of them, are the things we can control. But how can you really implement this one? That is my students, is kind of idea. I give these problems to the student, the graduate student, before I go to summer travels. And after I come back, the student come up with a very novel and interesting ideas, and that's his solutions. Okay, he look at the problems and started with a very special examples. So they consider all these things are the same, and the X follow a multivariate normal distribution, and they compute, okay, what is the reward function, and then find out, okay, by doing this max mean of reward function is related to the angle between beta and beta g. So everything can be translated to the angle length. Okay, beta g, that is the best decision for the G's group, and the beta is the overall decisions. I consider the angle between these two vectors, and then I can consider this minimax angle. They can show it's equivalent to your max mean of your reward function at this special case. And these minimax angles can be translated to this kind of projection ideas. I project beta to beta g, and I want to do this max mean, okay, projections. And it turns out, okay, in the literature, people studied since before. You consider the max mean correlations, okay, in these papers is a more mathematical papers, okay. People studied this kind of max mean correlation, and over, okay, this kind of idea is attached, okay, connected to this literature. And using these ideas, okay, and then after a little bit of deliberations, the students showed, okay, actually, if you use the minimax angle or max mean projections, it's equivalent to do this max mean reward functions. So we have these connections. After we show these connections, then it's very nice. I can do this minimax angle or max mean projection. They are equivalent. And after a little bit, okay, kind of formalizations, because the original problems is not concave, it's very difficult to solve globally. So we do a little bit of modification. Instead of maximize at the boundary of the unity ball, okay, we maximize within the whole unity ball, okay, make this tractable concave programming problems. And by doing that, then we have a very nice algorithms, okay. We can solve these problems, okay, using a quadratic constraint linear programming, the QCLP problems, doing this one, we can get the estimate for beta, then we can get the estimate for the threshold value functions. Okay, quickly, I think maybe I skipped this simulation, maybe a little bit about the simulation result. Okay, we compared the max mean method with the pooled method and average. Pooled method means you ignore the heterogeneity, pull the data together and estimate. And the average, you fit separate best treatment regime for each group. Then I take a simple average. Then I do this kind of studies. We have 4 different groups. Suppose I use other 3 groups to learn the treatment decision rule. I apply to this group to do the testings to see the value function and the PCD. You can see the maximum method for all these scenarios, okay, they give you the best decisions in terms of PCD, in terms of estimated value functions. So for this one, okay, for this data with heterogeneity, we see the benefit. And finally, go back to the schizophrenia data. So we do the same thing. This is from the 3 different geographical locations. I compare the max mean and the pooled data, and then report the estimated value functions. You can see using the max mean ideas, they give you larger, okay, value functions in each of the geographical locations. Compare you simply, okay, pull the data, okay, in this, okay, case. So this is the, okay, applications. Okay, finally, okay, we conclude, okay, the work. And so in this 3 projects, okay, we derive, okay, OTR, okay, decisions for different problems. And in currently our research, for simplicity, we only focus on the linear decision rules, okay, the function is the linear decision, but we want to extend it to a more complicated situations, allow the decision to be a complicated functions, okay, of your data. So currently, okay, my students are developing this flexible deep learning methods for this dynamic optimal treatment decisions, okay. That is one extension. Another extension is we want to develop the statistical and machine learning method for this optimal online decisions. This is not necessary to related to the medical decisions, can be also applied to other decisions like in the Uber, okay, system, the ride sharings, okay. How can you do this multi-agent, okay, online decision learning? Okay, that is one, okay, applications. And finally, okay, the research is supported by NIH, okay, PO1 grant. That is a bigger grant, okay, for this triangle area, the 3 universities, Duke, UNC, and NC State, okay. We are working on this cancer-related, okay, treatment prevention and treatment selection, okay, procedures. So the collaborators, okay, the first are my students, and then the last one is my collaborators, okay, the professor also in statistics department. Okay, thank you. So if you are interested, these are the reference of the 3 projects I presented today.
We have time for a couple of questions. Any questions?
Can you explain again the concordance idea here behind concordance? Because are the two patients refer to the same stratum or?
Let me see. Okay, allow me to screw up. Okay, so that's the concordance ideas. Okay, so can you rephrase can you say your question again? What is the
so
question?
here, I'm imagine that you have two patients, I and J.
Yeah.
If they belong to like different groups, being treated by different methods, then why this inequality makes sense comparing to just the
Okay.
the first traditional method.
Okay, so first this patient are from the same group. Okay, they are ID
Okay,
patients.
okay.
Okay, this one is not for handle heterogeneity data. That's for the same group. Okay, and then the original method directly target on value function. I want to maximize the value function, so they do this matching things. Okay, so if they are matched, they contribute to the estimation. If not, they're not. So we adjust by the propensity score on the weight. Okay. And our ideas, instead of just maximize the value functions, before that, okay, we want to make sure your treatment regimens satisfy this kind of concordance. That means when I rank the patients who should assign to treatment 1, who should assign treatment 0, we want to give them a ranking. Okay, using what? Using the index we found, using the beta x. Okay, if beta x is larger, these patients have more benefit to assign to treatment 1 compared to treatment 0. If I can give them this kind of natural rankings, then your treatment regimen just, okay, according to these rankings, just need to cut at which place. Okay, that cutoff point or threshold, we try to find using the value search. But in the beginning, the first step, we want to make sure this ranking is consistent, this concordance is preserved. So that's the major ideas. Okay, that's our major idea.
Replacing the first constraint?
Yeah, it's kind of more like alternative to just directly maximize the value. We add one more step, okay, to have a concordance first, okay, and then in the second step we still maximize the value. However, in that step, okay, you only need to maximize over one-dimensional parameter because beta x is already sorted. You just have one scalar cutoff point threshold to decide. Above this threshold, then it's treatment 1. Below this threshold is treatment 0. So even in the second step, we do the value search. It's a one-dimensional search. It's much easier than you search over all the space for p-dimensional. So that is another advantage when you add one step to this two-step. Okay.
One more question? Yes.
Is there a general benefit of converting the monotonicity into the concordance in constructing the objective functions? I see some other works, including my work, have saw some benefits of that.
Yeah.
So do you have knowledge about?
Yeah, that's a good question. They ask, okay, in general, whether there any benefit due to this, encourage this kind of monotonicity, okay, in here. And first thing I have to say, okay, that's the motivation from here, okay. We think, okay, we have this kind of monotonicities, okay, and then when we construct our treatment regimens, we want to preserve these monotonicities, and we find, okay, I didn't show here, okay, we found if they really have these monotonicities, move here, for example, so, okay, let me show you that is more from the model based, okay, that is from the last, okay, research project when we consider the statistical model, okay, the statistical model monotonicity in terms of what? In terms of here, the treatment effect. The treatment effect A times this precise function of a linear index. This precise function is a monotone. Means what? The larger the beta x, the better the y. This monotonicity is kind of assumed in the models. This monotonicity is very helpful to let us think about, okay, this beta x is a good prescriptive index, okay. If using this index, I can rank patients in terms of treatment decisions, okay? And then we also can show if this model is really true, this kind of concordance, okay, learnings, theoretically, okay, is the same as your value learning, okay? That means you maximize the value function is the same as you maximize the concordance functions as long as they have this monotonicity, okay, constraints. That is from this model, okay, kind of assumptions. However, from our experience, even your treatment effect don't have this monotonic statistic. But when you're doing your estimation, you add this kind of monotonic statistics, can help with your estimation accuracy and also can improve your performance. We don't have theoretical justification. We only have empirical study to show that even there's no monotonicity layer, but when you add this one to your estimations, still can help. Yeah.
All right. Okay. I have a question, but I'll ask it offline in the interest of time. Okay. Let's thank our speaker again. Thank you.
Thanks.
How do you validate? How do you validate